Okay. So that's the one. I'll start with this one and then
Give it
quickly,
to
and then we
We can.
see. Perfect. Okay. But not my one.
And this is mine.
Okay.
That one could go to your pocket.
Y esto. Sí, y después. Okay. Because we're broadcasting this live. It's a live stream, so yeah. This is for the whole world. It's a YouTube broadcast. Yeah. So now we're gonna. So watch out what you say. Everybody's listening to you. Ask good questions. Oh, maybe I should say that at the beginning. Good question. At least maybe for physics, it's a good. I don't know, but I thought of doing it, and they liked it. So the IT people.
Do we have the copyright to broadcast this?
He authorized us. He's a copywriter. You authorized us to broadcast this. Yeah. I wouldn't have done it without him. He's already had some.
Already with all kinds of variants of this talk on YouTube. So I said, however, I'm going to embarrass myself today. I probably already have.
Yes, I'm going to sit there. So thank you.
So how about the audience? The audience?
Oh, well.
We need permission to.
Yeah, whatever. As long as we don't make money with it, I think we're fine. Oh, that's. I guess we needed permission from the audience. Too late. Yeah. Oh, should I tell people that this is being live
Yes,
streamed at the
please.
beginning, right?
Yeah.
What is that? Oh, that's a laser. Oh, shoot! I'm sorry. Oh, I'm sorry. I was. So this is the thing, and so this is the laser. So this is the laser.
The laser right here.
Oh, laser
Yeah,
here.
all right, I got it.
Good. Sorry about that.
It's all right, it's fine.
One of the. Yeah. I've always. I say the same thing. I should get my own, right? Like you do. So I should start exactly at 2:30?
Yes. Well, it's already streaming because we started at 2:25.
Okay. Let me introduce you to Scott. Oh, okay. Sorry. So Scott, this is Kamanugu Narati, a colleague.
Hi, good to meet you.
Another of the nonlinear theorists that we have here. So
Cool.
yeah, you got a bunch of them at your place, right?
Yeah, I
In
mean,
physics,
yeah. So I'm in the CS department, but I do know some of the people in the physics department. I do hang out with them sometimes.
Yeah, Mike Martyr.
Oh, I don't know.
Interact with him much?
Oh, okay. Nice to meet you. Yeah,
Okay.
good to meet you too.
So we were actually. Hey, Rene, let me introduce you to Scott.
Hi.
This is
Hi, good to meet you. Nice to meet you.
He's an experimentalist in heavy ion.
Cool.
Competition. Yeah. Okay, awesome. Andre, why don't you sit there? So let me introduce you to. Andre,
Hi. Hi, I'm Scott. Good to meet you.
expert in active matter, kind of fancy,
Okay.
weird new statistics.
All right,
and
all right.
He's good, another good guy. Let's see. So,
Hi, I'm Scott. Good to meet you. All right. Thanks.
I think that's. I think I can. Okay, it's. All right, it's 2:30, and I wanted to let you know that we're live streaming this event. No, this is just for the one for live streaming. Yeah, there's no local. Yeah. So, well, I hope you can hear me. Is that okay? Anyway, you will be able to hear the speaker very well, I'm sure. So, first of all, there is a follow-up talk. Actually, I'll say it right now. Tomorrow in the math department. So, for those of you who want to, have even more of quantum computing and quantum information, you should also try to go to the one in math. Let me say that we have the great honor and pleasure to have been able to collapse the wave function of Dr. Scott Aaronson and finally come down to Houston. Dr. Anna Verchinina from math and I, are responsible for doing this. It's quite an achievement. Just to tell you where he's been in the last several weeks, we started corresponding kind of, getting towards this event a few weeks ago when he was in Davos, Switzerland. And then after that, he's been to Princeton, University of Waterloo in Canada, Berkeley, Harvard, MIT, and then us here. So we're quite fortunate that he's included us in his tour of the latest on quantum computing and quantum supremacy. To those of you who follow the subject, and I think many of you do, he's a well-known quantity, and I could spend a fraction of the talk at least talking about all his background and awards, etc. So I'll just say that he's one of the world leaders in quantum computing, quantum complexity, and certainly in terms of the latest events and in the field, I think there's probably nobody better to tell us the state of the art. Okay, so again, Scott, I'm very glad that you came. So he got his PhD at Berkeley University, and after that, he went for postdoctoral work at the Institute for Advanced Studies at Princeton, the University of Waterloo in Canada, then became a professor at MIT, and finally came to the University of Texas at Austin in 2016, where he's the David Bruton Jr. Centennial Professor of Computer Science, and he's the director of a new Quantum Information Institute. So one thing before I give him the mic is that for those of you who are planning to have children or have children, and right, or even grandchildren like me, I want to give you a piece of advice that I got from his Wikipedia page. Right, so when you have a babysitter at home, when you go out and have fun and your children are being babysat, make sure that person is taking at least a calculus class, right? Because that's how Scott got interested in learning calculus when he was 11 years old. He just looked at the book and it's just nice symbols. He was very intrigued about it and started learning calculus. So don't forget that. Okay, well, so we have the pleasure to have him now tell us about quantum computational supremacy and its applications. So without further ado,
right. Well, thank you, Carlos, for the introduction that I'm sure I can't live up to. But thanks for inviting me here. I've been wanting to come to UH since Anna and then Carlos got in touch with me, and really since I've been in Austin at all, and it's exciting, to see the level of interest in quantum information that there is in all over Texas, really. So, not to mention the rest of the world. This talk is called Quantum Computational Supremacy and its Applications. Now, when I did a Google image search for a quantum computer, this is one of the first things that came up. Now, it'll be clear from this talk that I am not an engineer. I was not part of the team of 75 people at Google that, did this remarkable achievement recently of building this 53-qubit chip, Sycamore, but, I have toured their lab where, so I know enough to tell you that that's not exactly what it looks like. Okay, so before we get started on sort of the new stuff, I thought that I should at least spend one slide to explain what quantum computing is, which is typically hard to do. Except the good news is I know that many of you are physics students or physics faculty, so that helps. I don't have to convince you that quantum mechanics is a real thing. In addition, I use the joke that we've learned a secret in quantum information science that quantum mechanics actually becomes much, much simpler once you take the physics out of it. Okay, if you actually want to know the ground states of interesting molecules, sure, that's complicated. But if you just want to know the underlying logic of the thing, enough to answer, let's say, most of the questions that a layperson would have about the subject, insofar as they are answerable. You really just mostly need to understand the logic of amplitudes and how they generalize probabilities. Okay, so you need to know a certain generalization of the rules of probability themselves. Okay, so the way that we, and I think of it as like less like physics than like an operating system that physics, was discovered to have to run on as application software. General relativity is hard to port to this operating system, but the rest of physics now runs on it. And a classical computer, we would say, has a state, a memory, which is made, we would typically imagine, of bits, ones and zeros. Right? If I have n bits, then the computer has 2 to the n possible states. And I can do a computation proceeds by my doing operations on the bits. Like I could flip a bit. I could say I want to flip this bit, but only if this other bit is a 1. So I can do conditional logic that causes bits to affect other bits. And then, to really be general, I could have a computer with probabilistic operations. I could say, for example, take this bit of the memory and set it to be 1 with probability 1/2. Okay, now there are different ways of getting a random number generator into a computer. Ironically, the most principled way is to use a quantum mechanical source. But we would still call it a classical computer if you're only using quantum mechanics in that kind of limited way. And I could say for example, set the first bit to be 0 or 1 with equal probabilities. And then if I wanted to use fluid imagery, I could say that the state of the computer branches into 2 parallel worlds, right? Or corresponding to each way that it could go. Or more soberly, I could say, well, my knowledge of the computer state is now represented by a vector of length 2 to the n. This is a vector of probabilities. Okay, I assign 1 probability to every possible configuration that the computer could be in. Okay, and now at the end, the computer's not useful unless I can look at it, right, and see an output. Okay, so I look at it, and now I'm going to see just one particular string, x. I'm not going to see the entire vector of probabilities, right? but I will be more likely to see strings that have a larger probability, okay? And the probability that I'll see a given output of my computer is just the sum over the probabilities over all the possible paths through sort of computation space that could have led to that output, right? Where for each path, the probability of that path is just the product of the probabilities of each of the choices that were made in following that path, right? And I've been pedantic about this because if you understood everything that I just said, then what is a quantum computer? It's just the same as I just said, except we're going to replace the probabilities by complex numbers, okay, which in quantum mechanics are called amplitudes, okay? And so now I can create quantum superposition states. Like I could say, you know, I want an amplitude of 1 over square root of 2 for, you know, my 2 bits in my computer's memory to both be 0. I want an amplitude of I over square root of 2 or something for, you know, the bits to be in the state 1, 0. And in general, I can do all kinds of norm-preserving linear transformations that would act non-trivially on only 1 or 2 of the bits at a time. You know, in quantum mechanics, we call these unitary transformations. Yeah, so you know, the basic building blocks of a quantum computer are, you know, these bits that can be in superpositions of 0 and 1 states, or, you know, what we call quantum bits or qubits. Okay, a qubit is just a bit that has an amplitude for being 0 and another amplitude for being 1, you know, where these are, you know, so it's in a complex linear combination of the 2 states. Okay, but now the key point about quantum computation that makes it interesting, that makes it potentially powerful, is that if I have n qubits, then, you know, quantum mechanics is unequivocal that in general I need a vector of 2 to the n amplitudes to describe its state. Okay, I need an amplitude for every possible configuration of all n of the qubits together. Okay, so you know, there's you know, so if there were 1,000 qubits, so, you know, which could be physically realized in many ways, but, you know, for example, 1,000 spin 1/2 particles interacting with each other, that's not a lot, and yet that gives rise to a state that requires 2 to the 1,000 power amplitudes, okay, which is more than could be written down in the observable universe. Okay, you know, but somehow it is there in our best description of nature. A quantum computer is a device that tries to exploit that. Okay, now almost every popular article that has ever been written about quantum computing, you know, has gone completely off the rails in trying to explain this. Okay, and the way that the specific way that they go off the rails is by saying, well, so a quantum computer is just like a classical computer, except it can try every possible answer in parallel, right? Just each answer is tried in another parallel universe or something, right? And now let me explain the problem with that. Okay, you can create a quantum superposition over all possible answers to a problem, even if there are exponentially many of them, even if there are 2 to the n possible answers. That's very easy to do. Trouble is, for, you know, at some point you've got to measure. You know, you've got to look at your computer and see what answer it's produced. And the famous Born rule of quantum mechanics says that the probability that I will see a given output when I look at a quantum state is equal to the squared absolute value of the amplitude of that state. Okay, the amplitude being just a sum of all these complex contributions. Okay, and so if I just created an equal superposition over all of the possible answers, then when I look, what I'll see will just be a random answer. Okay, well, if I just wanted a uniform random answer, I could have picked one myself and saved all the trouble of building a quantum computer. Okay, so the only hope of getting an actual advantage with a quantum computer, you know, the only purpose in running it is to exploit the way that these amplitudes, being complex numbers, work differently from classical probabilities. Okay, those of you who are physicists will know that the central difference is that amplitudes can interfere with each other and cancel each other out, right? As famously happens in the double slit experiment, for example, where I have some amplitude for a photon, let's say, to reach a certain spot on a screen, but it's a sum of two contributions. If one of those contributions is positive and the other is negative, they will cancel out. The amplitude will be 0, and therefore the probability will be 0. Okay, whereas if I had closed off one of the slits, then the amplitude will be positive or negative, and I can see the photon there. Okay, so by decreasing the number of ways for a thing to happen, I can increase the chance that it happens. Right? That is quantum interference in a nutshell. And Richard Feynman used to say that if you understand the double slit experiment, it contains all of quantum mechanics, right? And one illustration of that is that a quantum computer is in some sense just a massively scaled up double slit experiment, okay? It is a double slit experiment involving 2 to the n slits, if you would like, and a much, much more complicated choreographed interference pattern. But it is, with every quantum algorithm, you are trying to choreograph things in such a way that for each wrong answer, for each answer that you don't want to your computational problem, you have some paths leading to it that have positive amplitude, let's say, so other paths leading there that have negative amplitudes, or amplitudes pointing every which way in the complex plane, and the contributions all interfere destructively and cancel each other out. Okay? Whereas for the answers that you do want, we want constructive interference to happen. We want all the paths leading to those answers to have amplitudes that are pointing in the same direction. If we can arrange that, then when we measure the computer state, we will see the right answer with a large probability, right? And, we can always just keep repeating the computation several times, until we do see it, okay? And, but the tricky part is we have to do it faster than we could just solve the same problem with our classical computer. Otherwise, what's the point? Okay, and we've got to do that despite not knowing in advance which answer is the right one. Okay, and so that is sort of the bizarre hammer that nature has given us in the form of quantum mechanics. The job of quantum computer science is to figure out sort of which nails, if any, that hammer can hit. Okay, so there's a lot of discussion right now, as you might have noticed, about how to actually build quantum computers. Okay, so the sort of abstract logic of qubits that I talked about on the previous slide, right? You don't, in some sense, you don't have to sort of know anything about physics to, even master that, even make, do lots of quantum algorithms research, right? You could say any more than you have to know how a transistor works to program a classical computer or even be a virtuoso programmer, okay? But having said that, today, the quantum computing version of the transistor has not been invented yet. Okay, we are, optimistically, with the announcement of quantum supremacy a few months ago by the Google team, we are now finally entering the very, very early vacuum tube era of quantum computing. Okay, and there are a bunch of different approaches to trying to build, to physically realize programmable qubits that are all being pursued in parallel. No one knows yet which of the approaches will win, or whether it will be, none of them or some completely new approach. But some examples are I can have I can use the spin states of atomic nuclei as qubits. So I can just have ions, suspend them in a magnetic field, move them around with lasers. They have some Hamiltonian that, causes nearby ions to interact with each other. I can use that to engineer 2-qubit logic operations. Okay, that's the trapped ion approach being pursued by a startup company in Maryland called IonQ, also now by Honeywell. I can also use cold atoms. There's a group at Harvard led by Misha Lukin that's a leader in that. I could use the polarization states or other states of photons as qubits. This optical approach to quantum computing is being pursued by a startup in Palo Alto called PsiQuantum. All these startups I'm mentioning, right? None of this existed 5 years ago, okay? But this is, now it does. And and then Microsoft has placed this huge bet on something called topological quantum computing. Okay, this is, I would say, like a big gamble even by the standards of quantum computing, right? In the sense that, like, so far no one has managed to make even one topological qubit. Right now they're at 0 qubits with this approach, okay? If it works at all, there is a beautiful theory behind it that suggests that maybe it could scale much more easily to, thousands or millions of qubits. And that's why there's the excitement. To get it to work, all you have to do is create a new state of matter that's never been seen before. Okay? So, and then finally, there is the superconducting qubits approach. This is the one I think it's fair to say has had the greatest success so far. Okay, and this is the one that all of this recent news has been about. So this is where we build a chip. Like this is Google's Sycamore chip right here. It's the size of an ordinary computer chip, but on it are like 53 loops of wire that can store current in 2 different states, representing a 0 or a 1. The wires are connected via Josephson junctions, so that nearby, the qubits are arranged roughly in a 2D grid. The neighboring qubits can interact with each other. And what we do is we place this chip in a dilution refrigerator. That's this upside down wedding cake here. And it is cooled to about 10 millikelvin, a hundredth of a degree above absolute 0. And that causes the energy states of these currents to superconduct, to behave as qubits. And so now they can be in superposition states. Now, crucially, we can send control signals from a classical computer that is outside of the dilution fridge that tells each qubit exactly what to do when. Okay, so exactly which of the neighboring qubits it should interact with, and how so. In that sense, the device is programmable. Okay, and these qubits are enormous by the standards of qubits. By enormous, I mean you can see them with a magnifying glass. Okay, they are sort of macroscopic systems. They are only able to behave quantum mechanically at all because of the magic of superconductivity, right? And of course that only works, at least, with this kind of technology at extremely low temperatures. Yeah. Yeah. Through wires. And actually a big issue, I'm told, is the, decoherence, caused by those signals coming in, right? And that, that heats up, the chip, but unless the signals that are coming in are themselves carefully cooled down. Okay? So, but, sorry? They use the voltage? It's more complicated than that. It's like they pick like 2 orthogonal states in some Hilbert space of and they just define them as 0 and 1. And I don't think there's a good intuitive description of it. Okay, but so this will not be a talk about the hardware aspects of the chip. In fact, we've already nearly exhausted my knowledge of it. Okay, but but let me just step back and address the more general question of why is building a scalable quantum computer so damn hard, right? Such a famously hard problem. Well, the answer, in some sense, was understood since the very beginning of the field, 25, 30 years ago. And this is decoherence. Okay, this is unwanted interaction between the quantum computer and the entire rest of the world, basically, which has the effect of prematurely measuring the quantum computer state, forcing it back down to be behaving as a classical state. Okay, and decoherence is such a severe problem if you're trying to build a quantum computer that there were distinguished computer scientists and physicists in the 90s who said you will never overcome this, right? Just the laws of physics will not allow you to perfectly isolate qubits from their environment while also acting on them and also telling them exactly what you want them to do. And if you don't perfectly isolate them, then errors will just build up over time. They will eventually kill your computation, and and you're dead. Okay, so the great discovery in the mid to late 90s that changed the opinion of most people in this field was the discovery of quantum error correction and quantum fault tolerance. Okay, and basically what these said is that there are clever ways to take a qubit, a logical qubit that you care about, and encode it across the collective state of many physical qubits, okay, in such a way that the logical qubit is protected. Okay, so even if, let's say, 1% of the physical qubits were to lose their quantum coherence, that is, leak their zero-ness or their one-ness out into the environment, right, and lose their quantum superposition state, you can detect that has happened, that an error has happened, and you can recover the information, the superposition state that you need from the other 99% of the qubits, okay? And you can continually do this. And in this way, you can actually do an arbitrarily long quantum computation, with as many qubits as you need, even using unreliable parts, okay? As long, you don't have to have perfectly reliable, perfectly isolated qubits. You merely need really, really, really good qubits, right, that are, very, very, very well isolated, even if not perfectly so, okay? And basically what, the upshot of this whole theory was that there is a threshold, right? So as you lower the physical error rate of your qubits, right, initially everything you try to do to correct errors, to protect your qubits from the environment is only making things worse, okay? Because all your error correction machinery itself has error and so on, right? But when, the components pass a certain threshold of reliability, imagine like you've passed the threshold for a nuclear chain reaction, right? Now, at that point, each round of error correction makes things better, okay? Now you can use your physical qubits to simulate logical qubits that have a lower effective error rate than the physical qubits had. And then those logical qubits can themselves simulate, further qubits that will have a still lower error rate, and so on, right? So that, you get, in the limit, you get arbitrarily reliable qubits, okay? Now, long story short, we are not there yet, okay? The achievement of quantum supremacy, was with completely non-error corrected qubits. And fault tolerance. Well, there's going to be a race to achieve it. Over the next decade or decades. I'm not going to speculate on how long it's going to take. Okay, but this is what will be needed to achieve the real promise of the full promise, let's say, of quantum computing. Everyone agrees about that. Okay, this talk is about what we can do in the meantime. Okay, and that brings me to this phrase that I'm sure you've heard of quantum supremacy, right? And here I've shown a picture of my great friend, the physicist John Preskill, who coined this term in a paper in 2012. Although the idea goes back much earlier, even to like the beginnings of quantum computing in the 80s by Deutsch and Feynman. But anyway, I'm showing Preskill's picture here mostly because if you find the term quantum supremacy, either too bold or even offensive, there were people like saying we should change it because it has too many bad connotations. Anyway, if you have any of those concerns, I encourage you to blame him. Okay, don't blame me. So, I'm just going to, there have been proposed replacement terms, like one of them was quantum inimitability, inability to imitate, but how many people can pronounce that, right? I had to practice it, right? Another one was quantum ascendancy, but to me that just sounds like we're a UFO cult. We're ascending to some quantum computer in the sky. So I'm gonna use Pascal's term, but all right. But what he meant by it, and what I'll mean by it, is the use of a quantum computer to solve some well-defined problem much faster than any available classical computer on Earth today running any classical algorithm that we currently know. Okay? Now notice that I did not say anything here about it being a useful problem. Okay? Usefulness is not, necessary. Think of the Wright brothers airplane. Think of Fermi's nuclear chain reaction. Right? The goal is to prove a point, is to sort of prove that a certain, type of technological advantage is possible at all, not yet to actually do something useful with it. Okay? If we can, that's just a bonus. Okay, but what's important is that there is a well-defined task on which the quantum computer can actually outperform. You can compare the performance of a quantum to a classical computer at doing the same task, and where the quantum computer's performance is just clearly markedly better. Okay, that is what we've wanted to see, and. I think it was important to sort of accept no substitutes for that, and that is what Google now claims to have. Okay, so now just to clarify the concept, I would say that the problem, whatever problem we're going to use for quantum supremacy, it does need some definition that is sort of independent of the hardware that we are using to achieve it. Okay, so suppose someone came to us and they said, well, I have this chemical, this complicated molecule in my lab, and I can't solve it. I can't solve for its ground state with even the biggest supercomputer. So why can't I just define my molecule to be a computer that is achieving quantum supremacy for the problem of simulating itself? Okay. Well, I want to say that doesn't count. Okay. And the reason it doesn't count, first of all, we could say, well, this molecule is not programmable, right? It's only doing one thing, right? But even more deeply, we could say the thing, before I'm willing to count something as a computer, it has to be logically possible for it to output a wrong answer, right? If your job is just to simulate yourself, then by definition you will always succeed. Okay, a computer is something that should have some external standard of is it out producing a right answer or not, where you could compare it to that expectation and see if it is or it isn't. Okay, and so and that criterion will be satisfied, with what we're going to be talking about. It's related to sort of the programmability of the device, I would say, the ability to put many instances of some general mathematical problem onto it. And then, for me, I would say that to declare quantum supremacy really requires three things. We want to see an actual observed speed up, which means, we're doing something in a few seconds or in a few minutes that would, with like the biggest supercomputer on Earth, would at the very least require days, weeks, maybe years, maybe centuries, right? So we want to see that, in many orders of magnitude speed up. I don't care about a factor of 2 or 3. Then, in computer science, we don't really care that much about like specific numbers, like a speed up of a factor of 1,000 or 1,000,000. What we really care about are asymptotics. Okay, we care about the scaling behavior of algorithms. As your input were to get larger and larger, how is the running time increasing? Is it increasing as a polynomial in the size of the problem, or is it increasing exponentially with the size of the problem, right? It's because, this is ultimately what is going to govern what we can hope to solve at all with our computers, right? Like, if I have if I took, an algorithm that had exponential scaling and I replace it by one with polynomial scaling, then that could easily mean taking like an instance of that problem that previously I couldn't solve within the lifetime of the universe, okay, within, hundreds of billions of years, okay, and solving that problem in a few minutes instead, okay? That is what, that is why we care about polynomial versus exponential, because, that is what governs sort of speed-ups of that magnitude. Okay, so we want to see that we're actually taking something that was theoretically predicted to require exponential time for a classical computer and to be solvable in polynomial time with a quantum computer, right? In some sense, the entire point of a quantum computer is to change the asymptotic scaling behavior of certain problems, right? And so we want, the theory to sort of predict that. But then thirdly, I want the actual observed speed up to only be explainable in terms of the asymptotic scaling behavior, right? In other words, I want, like to do some computation, let's say with a 53 qubit quantum computer, to pick a random example, and and now for us to be able to say, look, the only explanation we have for how this computer produced the outputs that it did is that before we measured, it had a quantum state involving 2 to the 53 complex numbers, which is about 9 quadrillion. Okay, and any classical simulation that we currently know would require doing about 9 quadrillion calculations, but we got to take advantage of quantum mechanics. I would like to rule out any explanation other than that one. Okay? Yeah, I think that is really the thing that we are after here. Okay? Now, the way that I often like to put it is, what is the point of building a quantum computer, right? Well, people talk a lot about certain applications of quantum computing. There's, what you read about in the press is often quantum computers are good because they're going to revolutionize AI and machine learning and big data and optimization. I can tell you that, 90% of that is wildly overblown, okay? And, in fact, we know modest speed-ups that you can get with a quantum computer for those problems, but even with a perfect one, we probably only modest speed-ups, okay? Like solving them at about the square root of the number of steps that you would take classically. There is, much more dramatically, quantum computers could get huge speed-ups for simulating quantum mechanics itself, which is something of great industrial interest. If you're trying to design new drugs, new materials, new, superconductors, anything like that, right? I think that's probably the most important economic application of quantum computers that we know about, is just to use them to solve quantum mechanical problems. Okay, but the most notorious application that really put the field on people's radar was Shor's algorithm 26 years ago that said that a full scalable quantum computer, if and when it's built, could break almost all of the encryption that we currently use to secure the internet, right? Now, that's not because quantum computers could break every form of encryption. We don't think they can. It's just because we happen to use, crypto systems that are very vulnerable to quantum attack. Okay, which is itself a solvable problem, right? We could switch to quantum resistant forms of encryption, and there's already a push to do that. Okay, but for me, all of that is just icing on the cake. Okay, for me, there's been one overriding motivation for quantum computing since the very beginning, and that is simply disprove the people who said that quantum computing was not possible. Okay, I would just like to rub their faces in the reality of quantum mechanics. Okay, so here, you see some thing with, Bob Laughlin, Nobel laureate, Michel Alicki, Michel Diakonov, Robert Alicki, some famous computer scientists, Leonid Levin, Oded Goldreich, Gil Kalai. Now, like, if I were, now some quantum computing skeptics, so, say, okay, quantum supremacy, whatever, maybe you can do that, but, until you have error correction, you have nothing. right? And everyone knows that's the real question, right? If I were a skeptic, that's certainly the line that I would be taking right now, right? In fact, even if I had previously said that quantum supremacy could never be done, I would now be like, oh yeah, everyone knows that could be done, that, it doesn't matter, right? Gil Kalai, interestingly, is not saying that, right? So he's a famous mathematician who's been publishing articles for 15 years proving why quantum supremacy can never happen and why quantum computing can never happen, right? And he has said, the recent announcement by Google, if it's correct, that refutes his entire position. Okay, so which was a very honest thing for him to say. Now the conclusion he drew from that is, well, then Google must have made a mistake in its experiment. Okay, and so every day he is emailing the Google team asking for more of their raw data and CCing me. Okay, and I guess he's going to find a grad student who who knows how to code to go through this data. And each week or so he has a new thing that he's pinpointed as the flaw in the experiment, only to retract it later. Okay, and so look, I mean, in some sense, this is exactly what he should be doing. This is the way that science is supposed to work. I am glad that people are trying as hard as they can to shoot this down. Because, quantum supremacy, is not like landing someone on the moon, right? It's a goal that could be achieved and then unachieved later, right? If, classical algorithms were to sufficiently improve, even if classical hardware was to improve enough, right? It's about one thing beating another thing, right? And so, it's very important to try to shoot this down, and only if it stands for a long time, should it be sort of really fully accepted. Having said that, my goal is maybe less to maximize the good of science than just to try to be personally right. And okay, so that brings me finally to this recent announcement of quantum supremacy. You may have read articles, popular articles about, like these. Now, here, what happened was that Google was working since 2015 to do the first demonstration of quantum supremacy. In fact, they had a conversation in 2015 with me and with some other quantum computing theorists about what would be a convincing demonstration to try to do. Can they do it with the hardware that they're planning to build? Based on those conversations, they made a decision to sort of go ahead with a design that, looked natural to them, in the leaving the job to us to sort of adapt the theory that we had to the hardware that they were building, which, we said, well, we'll take that deal, right? And so we sort of knew that this was coming, we knew that at any rate they were going to try. We didn't know if they were going to succeed, but that Google was going to put its full might behind this goal, right? Which, at this, to actually scale qubits at this level is, and get to where the frontier now is like at least a couple $100 million. And, you could say the academic labs have mostly been priced out of this competition. Okay? But, Google was in it, and then, this past summer, they felt that they had achieved it. And so they said, we're not going to announce it by press conference. We're just going to submit our paper to Nature, do what we're supposed to do. So they did that, but then NASA had some co-authors on the paper, so NASA had to submit it for internal review. As part of that, someone accidentally posted the paper on NASA's public website. And then, they noticed, they took it down right away, but in the meantime, Google Alerts had found it. Okay, so Google was sort of too good for its own good. Okay, so then the Financial Times ran a story about it. Then all these other people ran stories about it. In the meantime, Google was still under Nature's embargo, and they couldn't comment on any of it. So that was where my blog kind of came in. So
I remember I sent you a message saying, "Is that for real?" And you replied 30 seconds later, "Yes."
Yeah. Well, okay. Well, yeah. So, I mean, this is, sort of, my blog. I mean, when 500 people email about something, then it becomes a blog post, right? And all right. So let's step back and let's talk about what Google claims to have done. So they built this chip called Sycamore that has 53 superconducting qubits with arranged in a two-dimensional grid with controllable nearest neighbor couplings. If you're wondering why 53 qubits, well, they built 54 and one of them didn't work. Okay. And now they use this chip to basically just sample from some probability distribution. Okay, so they output samples from a distribution that we could call D, except to be honest, the actual distribution that they're sampling from is not really D. It is like 0.998 times the uniform distribution. So in other words, just complete garbage noise, plus 0.002 times the distribution D that you want. Okay, so that looks bad, but the good news is that taking each sample is very fast. It can be done in about 40 microseconds, which means after a few minutes you can take millions of samples. Okay, and just by basic statistics, millions of samples are enough to extract even a signal that has a signal to noise ratio like this. That's like a 1 in 500. Okay, so that's what they did. They did a bunch of classical post-processing to, which we'll talk about later, to try to sort of prove that this signal was present. And then, crucially, they gave an argument that at least if you take the best classical algorithms that we currently know, and you ran them on the best supercomputer that they had access to, which had about 1 million cores, it would take about 10,000 years, okay, to get the similar results as what the quantum chip had produced. So that was the speed up that they were claiming, right? Now I should clarify that in the present state of theoretical computer science, there is no hope of proving a speed up, right? Proving a speed up would mean proving that there is no classical algorithm that could possibly give you the same output in a similar amount of time. Okay, but unfortunately we just do not know how to prove impossibility theorems of that kind. If any of you have heard of the P versus NP problem, okay, it's similar to that. Okay, it's in fact directly related to that. Okay, what we know how to do in theoretical computer science is pass the blame to other people. Okay, so we know to show, look, I can't prove that this problem is hard, but if it were easy, then here's 1,000 other problems that would also be easy. Okay, so you should probably trust me if I tell you that it's hard. Okay, we know how to prove things like that. Okay, and so and this is exactly what we tried to do. The theoretical work that because I and others did that sort of led up to this experiment was mostly about that, about trying to give complexity theoretic evidence for the hardness of these sampling tasks. Do you have a question? Yeah. Yeah. Well, it's not. It is not. That would just be you if they were completely random. Okay, I'm now going to come. Let me address that in the next couple slides. Okay, because the crucial point is that these numbers are biased random numbers with very specific biases that we are going to be looking for as the signal of the quantum nature of the device. Okay. Yes. So in fact, what we can show is that. Okay. So let me address that on this slide. Okay. An interesting question is what should we do to best achieve most easily achieve quantum supremacy, right? And and some people, okay, the obvious thing would be just use Shor's algorithm to factor a 2,000-bit integer, right? And then that, once it's factored, then you can just check the prime factors for yourself, right? You can check that they work. It's clear if the answer was right or not, right? That's like the gold standard. Unfortunately, we're still very, very far from building the kind of fault-tolerant, error-corrected quantum computer that would be able to do such things. Okay, same with using Grover's algorithm for search. Same with even most quantum chemistry simulations. And in any case, the theoretical evidence that these things are hard is actually not nearly as strong as we would like. That they're hard for classical computers, right? Like some number theorists believe there might well be a fast classical factoring algorithm, right? We base the security of the internet on the belief that there's not one, but for a mathematician that doesn't count for much. Okay, so so now but a sort of a different idea sort of emerged from over the last decade or so or more, and this was to there is a huge number of advantages to switching from problems like factoring with a single right answer to sampling problems. Okay, that is problems where the desired output is a sample from a target probability distribution. So, there is an enormous number of possible outputs, right? The criterion of success is going to be a statistical one. Are the outputs sort of biased in the correct way? Okay, but again, we're going to be doing the same thing, just comparing what the quantum computer does to what a classical computer that was equipped with a random number generator can do. Okay, we are going to accept nothing less than a separation between those two. Okay, so we're still asking the same question. Okay, but the idea of looking at sampling problems in this context, as far as I know, was first mooted in a prescient 2004 paper by Barbara Turhall and David DiVincenzo. The modern push to actually do this type of experiment with, technologies of the near future started with two papers in 2011. One was by me and Alex Arkhipov, and it was about a proposal to do this with optical devices that we called boson sampling. Okay, and the other one was due to Bremner, Joza, and Shepard, and that was to do it in something that they called the commuting Hamiltonians model. Okay, now in both of these papers, kind of the sort of crucial observation that we made is that the amplitudes of even very simple quantum systems can be incredibly hard quantities if you have to calculate them exactly. In fact, they're called Sharp-B hard quantities. Okay, now that doesn't mean that a quantum computer can solve a Sharp-B hard problem. The reason why it doesn't mean that is that amplitudes are not directly observable. Okay, so you don't get to just see an amplitude, right, in your quantum circuit. But if I can sample from a probability distribution that is defined by these super hard to calculate amplitudes, these Sharp-B hard amplitudes, then that already, we can argue can go beyond what a classical computer would be able to do. Okay, so we were able to prove theorems to the effect that if you had an efficient classical algorithm that could sample from exactly the same probability distributions that these quantum devices were sampling from, then that would cause something called the collapse of the polynomial hierarchy. Okay, now if you don't know what that means, you could take my word for it that it's bad. But like if you know like what it would mean with like P equal to NP, right, which would be like the most titanic thing that could happen in computer science. The polynomial hierarchy collapsing is like not quite that, but it's kind of like the next worst thing. It's like the second worst thing that could happen. Okay, so it is like in the present state of computer science, it's about it's about the most ironclad evidence you can get that something requires exponential time. Something is hard, right? So. Okay, but now admittedly, this was not, this did not directly answer the physically relevant questions because you could say, well, look, in real life, our devices will always have noise and error. They won't sample from exactly the right distribution. And so now, really we should be asking how hard would it be for a classical computer to sample from approximately these distributions. And it's even worse than that because, you never observe what distribution is being sampled, right? These are distributions over enormous numbers of strings, like 2 to the n of them, okay? And so, you probably never see the same sample twice, right? And so the best you can do is you can do statistics on the outcomes that you do see. You can apply some tests to them to see are they correlated with the outcomes that are they sort of biased in the way that you expected. But now, as soon as you've specified your test, then, you have to say, well, what about a classical algorithm that just tried to cheat that test, right? is that a hard problem for a classical computer? Okay, so these are all the questions that we've tried to address over the last decade. Yeah, yeah. Not in general, no. You can approximate. What you can do is this is a very important distinction. You can approximate sharp P hard sums of non-negative terms. But now because this is quantum mechanics, we're dealing with sums of complex numbers. Okay? We're dealing with sums of, positive and negative and generally complex numbers that mostly cancel each other out. Now, what we're interested in estimating is the tiny residue that is left over. Monte Carlo is not going to help you with that. Okay, that is absolutely crucial here.
So there is a separation there.
Yeah, well, under some plausible complexity assumption, like the polynomial hierarchy does not collapse. Yes, that's exactly what we did. Yeah. So, so the advantages of looking at these sampling problems are, first of all, they're sort of much closer to what the hardware sort of naturally does. It's kind of like if you wanted to prove that chimpanzees were intelligent, you might be able to teach them to do arithmetic, right? But it's probably easier to just watch them in their natural habitat, right? Well, sampling problems are kind of like the natural habitat of a quantum computer. And we can get, even better confidence, arguably, than we had in in these cases, that these things really are hard for classical computers. Okay? The disadvantages, well, until very, very recently, we could not think of any applications for these things, except disproving the skeptics. And there's an ironic issue about how to check the results. Okay, so, these are experiments that are very much designed for, let's say, the 50-qubit quantum computers of the, present or, the very near future. You would not want to do these experiments with a 100-qubit quantum computer. Okay, why not? Well, because the only way we know how to verify it with, how to verify the answers with an n-qubit quantum computer is by doing a 2 to the n time classical computation. Okay, so 2 to the 50th is just at the, the outer limits of what we can do with supercomputers today. Okay, 2 to the 100th is way beyond that. Okay, so even with 100 qubits, even if you did it correctly, like we could never prove it, right? So you need to get a big speed up, but not such a big speed up that you can't classically verify the answer. Yeah. I don't know what you mean by robustness. Yeah, but again, these are sampling problems. You will never see the same answer twice, even if the computer is working perfectly. Okay, I cannot stress that enough. Okay, they're sampling problems. Okay, and so what you have to do is you have to do statistics on the samples that you see to see whether they have the patterns that you expect. Okay, so in a little more detail, what in the experiment Google did, the quantum computer is challenged by sending it a random, giving it a randomly generated quantum circuit, let's say C, on n qubits. Okay, so this is just a sequence of unitary interactions between neighboring qubits. They are staggered like this, in such a way that, like, after, we interleave some of these layers, every qubit is able to sort of influence every other qubit, right, is able to sort of get a signal to it. In the hardest circuits that Google did, there were about 20 of these layers, okay? And the interactions are just sort of chosen randomly, but then they're hardwired. So we could run the exact same circuit, again, another time with like the exact same initial state, typically just the all zeros initial state. And, and then we get multiple samples from the same distribution, right? So each time we do this, we create some highly entangled quantum state on 53 qubits, right, involving 2 to the 53 amplitudes. We then measure that state. We measure each of the qubits to ask it whether it is 0 or 1. That collapses the state. And that gives us a sample from a distribution over 53-bit strings, okay, in which each string has a probability that is the squared absolute value of its amplitude. Right, so we get all of these samples that are supposed to be from this distribution. Let's say there are k samples, so each s sub I is an n-bit string, and then we have to do a statistical test to check, like, are these samples consistent with having been drawn from our hard distribution? Okay, so the test that Google did is, almost the simplest thing that you could write down. They called it the linear cross-entropy benchmark. Don't worry about the name. Okay, all that the test means is that with our classical computer, we calculate what was the predicted probability with an ideal quantum computer for each of the outcomes that we saw. Right, let's say that K is like 1 million. So there's 1 million of these samples. For each one, I calculate using 2 to the n times brute force on my classical computer, just what was supposed to be its probability, and I add them all up. And the quantum computer is judged to have succeeded if and only if this sum exceeds a certain threshold. Okay? Now, what should be that threshold? Well, intuitively, if I was just picking strings completely at random, right, which would be the trivial, the stupid thing to do, okay, then each of these terms would be about 2 to the minus n on average. Right, there's 2 to the n strings, right, average probability, 2 to the minus n. Okay, so I add them all up, I would get about k over 2 to the n. Okay? Now, what if I had a perfect quantum computer? Well, then, it's a calculation you have to do. You approximate the amplitudes as Gaussian random variables. The absolute squares give you exponentially distributed positive real numbers, and then it's some integral, and then I have to try to remember from my babysitter's textbook or whatever how to do an integral, but fortunately it's one that even I as a computer scientist can still do, and you get the answer 2, which means with an ideal quantum computer you expect a value of this sum that is like 2k over 2 to the n. Okay, which means, intuitively, the better our quantum computer is working, the more the outputs that we will see are going to be biased toward the ones that were supposed to be likelier. Okay, right, so it is crucial here that the desired distribution over these strings SI is not uniform. Some strings, all the strings are exponentially unlikely, but some of them are supposed to be twice as unlikely as others, or 3 times as unlikely, whatever. And so this gives us non-uniformities that we can check for. Okay, we can check whether the S sub i's are preferentially concentrated among the ones that are supposed to be likelier. That is what we do, okay? That's the linear cross-entropy benchmark. With a perfect quantum computer, we would get a value of this sum that was like 2k over 2 to the n, so B equals 2. If you're wondering, in Google's experiment, the result that they've reported is B equals 1.002. Okay? So you may notice that is far from the ideal value of 2. On the other hand, it is greater than the trivial value of 1, and they were able to take enough data to prove that 1.002 is really not 1. It's really more than 1. Okay? So, if any of you know the history of the Bell inequality, of experiments that violate the Bell inequality, it's very analogous to that. Very analogous. Okay, so John Martinez, who is the head of the team at Google, likes to use the analogy of speckle. So like if I took a laser pointer like this one, I sent it through some ground glass, I would see some, garbage like this, okay? But basically, there are sort of red spots where there was more constructive interference of amplitudes among all the paths that a photon could take to reach those spots. Then there are sort of darker spots where there was more destructive interference among all the paths that the photon could take. Okay, but if I just shot a bunch of photons, boom, boom, one by one, I could check whether they were really going through that same network of ground glass by checking, are they preferentially landing on the redder spots in this picture? And in some sense, that's what we're doing, except now this, picture would have size, would have 9 quadrillion pixels in it. Okay? So some of you may have seen that after Google, actually before even the paper was officially published in Nature, IBM, which has been Google's main competitor in superconducting qubits, put out a rebuttal. Okay, so their initial rebuttal was, we reject the entire concept of quantum supremacy, right? All we care about is solving problems practical problems faster for our customers, okay? And to me, it was like, well, okay, but before you do something faster and useful, you prove you can do something faster at all. Like, that just seems obvious, right? But, then they sort of, a few weeks later, they put out maybe a stronger response, which was, well, we don't think Google achieved quantum supremacy anyway. Okay, and here was their argument. They said, look, if you take the largest supercomputer that currently exists on Earth, which is called Stampede, which IBM installed a year ago at Oak Ridge National Lab. That's why they know all about it. This thing fills 2 basketball courts. It's got, 100,000 cores. More relevantly for us, it has 250 petabytes of hard disk. Okay, they said that's actually enough hard disk that you could take these 2 to the 53 amplitudes, these complex numbers, and just explicitly write them all to disk. Okay? And once you had just written the entire quantum state to hard disk, then it would take you only about 2.5 days to simulate Google's device. Okay? Which you may notice is better than 10,000 years. Right? Now they didn't actually do this. This thing is being used for like nuclear weapon simulations, right? They can't just commandeer it to prove, to like score a point against Google, okay? But if we did, okay, and so I'm willing to accept for something like that would probably work. Now my response is simply, well, as long as that is the strongest response, then you could say it is kind of like the Kasparov versus Deep Blue chess match in the 90s, except with the historic irony that IBM is now in the role of Kasparov. Right? So in other words, like with heroic effort, you can just barely not quite match what the chip is doing, right, with the largest supercomputer on the planet. And the very fact that that's, if it's a close race now, then that reliably means that in a year or two it won't be, right? And in fact, there's even a silver lining here for Google. Google could not directly verify its hardest circuits. It had to rely on extrapolations from easier cases, right? But now that IBM has published this, Google can say, well, this is great news. IBM, you go and you verify our hardest circuits for us. Okay, so all right, well, I'm running out of time, but I did have some slides about the sort of theoretical work that we did. As I said, we studied like what are the best classical algorithms for simulating arbitrary quantum circuits. And if we want to be confident that this really is quantum supremacy, then this is sort of a crucial question to understand. And there are different trade-offs that you can get between the amount of time and the amount of memory, which was like exactly what was at issue in like Google's classical simulation of its circuits versus IBM's, right? IBM did what I call the Schrodinger simulation that requires 2 to the n time, where n is the number of qubits, but also 2 to the n memory, right? And this is crucial, right? With like 60 qubits, already this, IBM approach would not fit on the Summit supercomputer, right? You'd need like a whole city full of Summits, with 70 qubits, forget it, okay? And then there are approaches that can get by with much less memory, including one that my student Li Chen and I proposed a few years ago. The trouble is that these need even more than 2 to the n time. You need time that can grow like the depth of the circuit, like the number of gates in the circuit. Okay, if you're Google, you can do 2 to the 50th, but like let's say there are 1,000 gates in these circuits, even Google cannot do 2 to the 1,000. Okay, how do I know that? Because it exceeds a Google. Right. Okay. So, okay. Now, of course, we want evidence, of a more theoretical kind than just, we looked at the best algorithms and they're not good enough, right? So we did give some reduction evidence in the same paper by me and Li Chen, and which studied a different statistical test than the one that Google applied. And then recently, a UT undergrad named Sam Gunn and I wrote a follow-up paper where we directly analyzed how hard would it be for a classical computer to spoof the statistical test that Google applied to its data, right? And basically, we prove a theorem that basically says if there were a classical algorithm to spoof this test quickly, like in using much better than a brute force amount of time, Then there would also be a fast classical algorithm to take a random quantum circuit and estimate a specific amplitude with some variance that is slightly better than the variance of the trivial estimator that just always guess the same thing, right? So if you think that estimating general amplitudes in arbitrary quantum circuits is hard, then, then spoofing Google's linear cross entropy test should also be hard. Okay, that's and this sort of explains why the best spoofing algorithms we know of really are algorithms for these completely general problems of simulating a quantum circuit, where at least today there seems to be a 2 to the n barrier. And as long as there's that barrier, then you have quantum supremacy. So I won't go through how we prove this theorem. The sort of last point that I wanted to make was, that until very recently, there was a sort of an accurate sneer that you could make against these sampling-based quantum supremacy experiments. And that was, well, look, even if they prove some intellectual point about, quantum mechanics being hard to simulate with classical computers, it's all completely useless. Right? Because all you're going to get out, even if the experiment works perfectly, are a bunch of random bits. Right? Here's what some random bits look like if you haven't seen any. Okay? I got these from random.org. Okay? But they're not. So from the quantum computer, they're not uniformly random. Right? The deviations from uniformity were the crucial thing that we were looking for. But it takes heroic effort to even notice those deviations. Right? So what good are a bunch of random-looking bits? Okay, now a new idea that I had a couple years ago is that random bits actually are not completely useless, particularly if you can prove to a skeptic that they must be random. Okay, that has all kinds of uses. In particular, running a lottery would be a well-known example. Deciding which precincts to audit in an election, or proof-of-stake cryptocurrencies, right? Which are these things that try to get the advantages of Bitcoin without using 1% of the world's electricity to uselessly invert a hash function. Okay, but proof-of-stake cryptocurrencies require a huge source of random numbers that everyone can agree, even over the internet, must have been generated randomly, right? Now, it's completely trivial to use quantum mechanics to generate random bits, right? You just send a bunch of photons through a beam splitter or something, right? There you go, random bits. But that's assuming that you know and you trust the hardware, right? If you go to randombitsforyou.com, and they say, oh yeah, we totally use the best quantum mechanics to generate these bits. We totally promise you that the NSA has not backdoored us, even though they backdoored lots of similar things in the past, and we know that from Snowden and from so on, right? Why should you trust them, right? That is the problem that we are trying to solve here. Okay, and the observation I made was that basically as soon as you can do these sampling-based quantum supremacy experiments like the one that Google did, then you sort of automatically, as a byproduct, you get a computational guarantee of randomness. Okay, because even a quantum computer should not have been able to quickly give you samples that pass the linear cross-entropy benchmark, except by just sampling them in the quantum mechanical way, in which case it is also giving you bits that have a lot of true entropy in them, right? And you can then process that entropy in order to extract nearly pure randomness for use in cryptographic applications using known classical methods in computer science. Okay, so this is the first thing in my career that I've ever, or UT Austin ever patented, and so it's licensed to Google now, which is now working to demonstrate this along with NIST. We've not gotten rich from it. But, and it's not clear if it will really find applications, but, it might, it's not, in any case, it is far from the best application for a quantum computer, but with the technologies that, with the hardware that already exists, it may be the only application that is achievable. Okay, and that's why Google is now trying to demonstrate it. So where to go next? I think it would be really exciting to replicate Google's result in other hardware platforms with higher fidelity, more qubits, and so on. It's really important for people to try to design new classical simulation algorithms. in whatever regime they can. The fact that we've made discoveries recently means that, we have not exhausted this subject, right? And on the other direction, just get better theoretical evidence for the hardness of these problems, right? For the hardness of classically spoofing these quantum supremacy experiments. Is there a way to do quantum supremacy with a near-term quantum computer in such a way that a classical computer can just easily verify the answer? We know how to do that with eventual fault-tolerant quantum computers. We do not know how to do that with devices of the near future. And I think that this has sort of risen to become one of the central theoretical open problems in this whole area. And then there are many questions about my certified randomness scheme, how to actually get a reasonable rate of random bits in order to make it more practical. Like, could we get more and more bits by rerunning with the same circuit C over and over? So conclusions. Google has apparently achieved quantum computational supremacy using random circuit sampling on 53 qubits, building on a lot of the useless complexity theory that we did over the last decade. Even if true, this leaves the huge challenges of scalability and fault tolerance, but I think it already refutes those, like Gil Kalai, who said that quantum speedups were impossible. It was thought obvious for years that sampling-based supremacy experiments had no applications. My certified randomness protocol might change that, although many challenges remain in making it practical. Thanks for your attention. I'm sorry for going over. Thanks for listening. Yeah. Yeah, sure.
Terrific. So, we'll take some questions now. So, you pointed out that one of the applications of quantum computing is to quantum computation.
Sorry, to do quantum simulation?
Yeah.
Yes.
So, couldn't you do that and check it against an experiment rather than a...
Oh yeah, absolutely, absolutely. In fact, that is one of the big hopes for the next decade, that you'll be able to just do quantum simulations and check the result, not with a classical computer, but with an experiment.
That's one of the Texas Computing Institute. That's one of the big
Yeah. Uh-huh. Like the stuff that the Lucan group at Harvard is doing is already like that, right? They're already doing things that are like that, except not with like programmable devices, right? With like devices that you build just to do one computation only. Oh. Yeah?
So physical quantum states are not random vectors. They have some special properties. They may have low entanglement, or they have evolved from something that has a low entanglement.
Yeah.
So just to make sure I understand this quantum
Yeah.
So if I feed a 50 qubit state into Google's machine, will it be able to tell me whether that is a physical state or not?
So first of all, when you say physical state, right, I think what you really mean are like the ground states of Hamiltonians, right, that we know how to, but you mean stationary states, right? And this is emphatically not what we are talking about here, okay? So I can tell you what kind of state we're talking about here, and presumably it is physical because Google did it. Okay, they created it, right? So we don't have to argue about is it physical or not, right? And so, they are the output states of applying these random quantum circuits. Now, what they look, they look as if they were Haar random states. In other words, just chosen, uniformly at random from the 2 to the n dimensional unit sphere, right? In which case, like, each amplitude looks like an independent Gaussian random variable, right? That's what they look like. Now, they're not, we know that they're not really Haar random, and the reason we know that is that, Haar random states have way too many degrees of freedom, right? Like a small circuit just does not have nearly enough free parameters to get you to Haar randomness. But statistically, for almost all purposes we care about, they behave as though they were Haar random, right? So these are highly, the entanglement across any cut will be nearly maximal, not quite, right? But, it'll be close to maximal, right? The state will look as if it is Haar random. That is the kind of state that we're dealing with here. Yeah. Sure. Yeah.
So you said that the sample distribution is sort of a uniform distribution with a small deviation.
Right.
So what's
That's
the
right.
problem with setting any given distribution? Any given distribution is
Oh, well, the issue is, we would love to just get the distribution D, but we can't get that because of the noise in the circuit, okay? The noise in the circuit, so basically the amount of signal, until you have, see, this is exactly why we need error correction, right? Until you have error correction, the level of signal that you get is going to go down exponentially with the depth of the circuit. Okay, and we know that, right? And so basically, what that means heuristically is that the actual distribution you'll be sampling will look like 1 minus epsilon times the uniform distribution plus epsilon times the distribution D that you want, where epsilon is 1 over exponential in the circuit depth. Okay? So this is, this is not, we're not getting this because we want it. We're getting this because this is what you can get, if you don't have error correction. And, Google's achievement was to engineer something with 53 qubits where epsilon, although it's small, 1 over 500 in that case, it is not so small that you can't detect it. And they did detect it. Yeah.
Yeah. Before you mentioned that technically we cannot prove the quantumness of quantum computers with two magnitudes.
Well, right. We can't prove that they did the thing that they were supposed to. This is specifically an issue with these sampling experiments, right? With other types of quantum computations, you could easily verify the answer.
So
Yeah.
there's not still a hold on building more and more.
No. It's just that, you can scale up to 100 qubits, 200 qubits, but you'll have to look for other interesting things to do with them besides these sampling experiments, right? Unless people can figure out how to modify these sampling experiments so that the answers can be easily verified.
So currently we don't have on verifying how if a quantum computer does its job in a good way.
Well, there is no theoretical obstruction, right? Like if you take the example of, it all depends on what problem we are talking about, right? So if you take the example of the factoring problem, right, doesn't matter how large a number is. It is easy to check, anyone who claims to have factored it, right? You just check whether those prime factors actually are prime, which we know how to do. You check whether they multiply to the original number, right? So factoring, like there would be no limit on the size where you could verify, right? There is an amazing recent theoretical work by Urmila Mahadev, who is now at Caltech. And what she has shown is that in the eventual fault-tolerant era, you can take any quantum computation, and by using very clever cryptographic ideas, you can have it prove what it's doing to a classical skeptic. Okay? So Urmila has shown that in principle, in the eventual fault-tolerant era, there is a cryptographic solution to this general problem of a quantum computer proving what it did to a classical skeptic, okay? The problem is now about the near-term quantum computers, right? Urmila's protocol, we're not going to be able to implement it with fewer than, let's say, 1,000 qubits, right? And, so the question is, what can we do with 100 or 200 qubits that is interesting, where we can recognize somehow that the answer is right, but we also could not have gotten that answer ourselves. And, that's going to be a big thing that people are going to be studying over the next decade. Yeah. Yeah. Yeah.
It looks like there are two factors here. One would be time, physical time, but
Uh-huh.
like how does the system scale with the number of system
Yeah.
size?
Yeah.
So for example, if Google would build a computer 1,000 times bigger, and then now they can do something instead of 3.5 days, takes maybe a couple of weeks.
Mhm.
The supremacy clause.
Yeah, right. So we should all be clear that like quantum supremacy, as I said, it is not like a crisp milestone like landing on the moon, right? It is a little bit more like the moment when computers first outperform humans at chess, which, it was sometime between 1996 and 1997 or so, right? But you can debate exactly when in the Kasparov versus Deep Blue or, whatever, or even before that or after that, you think that milestone was reached, right? So it is more like that, okay? It is, but the goal is to get something that's on a scaling trajectory where, eventually, like I don't want to have to squint at it and argue about it, right? I want it to be on a trajectory where, like, even if you have to squint right now, it is obvious that in 2 more years there's no argument, right? Okay, right? So that, that is like, so like a lot of people get really, really into hair splitting the definitions, and I always try to get them to zoom out and just focus on the reality, of what is happening, right? But what I want to rule, what I do want to rule out with a definition is, I don't know if you've heard of D-Wave, right? They're this startup company that for years and years sort of was claiming to get all these speed ups with quantum computers, where most of us in the field felt that it is not real, okay? In the sense that a classical computer can easily do the same things, and they're just obfuscating that fact, right? Just over and over and over again, obfuscating it, okay? But sometimes you can get things that look like speed ups just because you have built some special purpose piece of hardware. And when you build special purpose hardware, it is often really, really good at the problem of simulating itself. Even better than a supercomputer would be. It's simulating this special piece of hardware, right? And so you can often do things that look impressive, but they might have nothing to do with that device being a quantum computer, right? They might have nothing to do with quantum mechanics, okay? And so, that became a big issue in the debate about D-Wave, and I am not interested in speed-ups of that kind. Right, I want to be very clear that I only care about the asymptotic kind of speed up. Okay. Yeah, sure. Okay, sure, no problem. Yeah, sure. Hey.